Linux Application Programming Series, Session 9, Programming with Pipes. This session is about the pipe which you have been using in Linux. Any serious user in Linux cannot survive without the vertical bar, the pipe. So agenda of the session is review of pipe model of inter-process communication, difference between anonymous pipes and named pipes, creating anonymous and named pipes, communicating through pipes, command line creation and use of pipes. So what you will see, this is all about pipes. So by the end of this session, what you can expect is, I know few things about pipe, or I was well aware of many things. After this session, you should be able to say that yeah, there were a few new things, or there are a lot of new things, but nobody will say that the entire topic was new for me, because the piping somewhere, I'm sure you might have used it in some part of your project and some usage of Linux. So in this session we'll explore Linux pipes. The pipe model is an older but still useful mechanism for inter-process communication. We'll look at what are known as half-duplex pipes and also named pipes. Each offers a FIFO queue model, that is a first in first out queue model, to permit communication between processes. The pipe model. One way to visualize a pipe is a one-way connector between two entities. For example, ls-l, piping symbol, wc-l. So this command creates two processes, one for ls-l and another for wc-l. It then connects the two together by setting the standard input of the second process, that is wc-l. Second process wc-l to the standard output of the first process, which is ls-l. This has the effect of counting the number of files in the current subdirectory in this particular case. So ls-l is executed. Whatever the output is, that is sent to the pipe. This vertical bar is representing the pipe, and then the wc-l command is there, which is taking input from this pipe and then sending the output to the terminal. Our command sets up a pipeline between two Linux commands. The ls generate output that is used as input to the second command, that is wc. This is half-duplex pipe, as communication occurs in one direction only. The linkage between the two commands is facilitated by Linux kernel, which takes care of connecting the two together. We can achieve this as well in applications. A pipe or half-duplex pipe provides the means for a process to communicate with one of its ancestral sub-processes. This is because there is no way in the operating system to locate the pipe. We call this pipe as anonymous pipe. It's most common to use is to create a pipe at a parent process and then pass the pipe to the child process so that they can communicate. From parent to child process passing information. Note that in a full duplex communication, when we have two-way communication, if that is required, the socket API should be considered instead of pipe. That allows two-way communication. Another type of pipe is called named pipe. The named pipe that works like a regular pipe but exists in the file system so that any process can find it. That means they have a name. This means that the processes not of the same ancestry are able to communicate with one another using a named pipe. So far what we have understood is something very basic which we have been using, and there is nothing new about that. And then there is something specific which is a named pipe, a new concept which is not as common as a Linux user, but yes, as a programmer we know it, that we have to have that. Now this is a simple pipe example, pipe1.c program in session 9 directory under source directory. So constant character string, this is a simple message, integer size, then integer my pipe. We are creating pipes here, and the buffer to hold the data, memory set, size of buffer, and then create the pipe. This is how we are creating the pipe. R80, that is integer, we are setting the value of integer, that is pipe number. Calling by the function, we are calling the function pipe, my pipe. So this is creating a named pipe. If we are not able to create it, if we are able to create it, then what? If it is equal to 0, then we are writing to my pipe. That means if the value is 0, it is successful. If not successful, then we are simply returning from the function, returning from the program. In this example, we will create a pipe within a process, write a message to it, and read the message back from the pipe, and then display it or emit it. We create our pipe using the pipe call at line number 19, which is used here, line number 19. This is how it is going to be created. We are creating a my pipe with this name. We are using a write function to write to this, and the content goes to the pipe. This is done by my pipe first one, my first program. I am in first content, and then it is sending the pipe data to my pipe 1 or my pipe 0, and it is reading from this. So we are creating our pipe using pipe call. We pass in a two-dimensional integer array that represent our pipe. This pipe is a pair of separate file descriptors. That is, pipe 1 is for output, and pipe 0 is for input, to take the input from. The pipe API function returns 0 on success, as is tested in line number 20. On return, my pipe array will contain two file descriptors representing the input to the pipe, that is pipe 1, and the output from the pipe, that is pipe 0 element number. The pipe 1.c, if you consider the same program, understanding, at line number 22, we are writing our message. Write my pipe, standard output, string. What is the value of the string? What is defined here? String, we set the string here, constant character string. We are writing that message to this pipe, and the length of the string is, size of the message is string length function, normal function. The pipe now contains our message that can be read at line number 25 using the read function from the pipe. So line number 25, bytes read equal to read my pipe, pipe stdin, and buffer. So we are reading into the buffer, the size is max line, that is 80 characters. Here, from the perspective of the application, we use the stdin descriptor to read from the pipe. The read function stores what is read from the pipe in the buffer variable, that is argument number 3 of the read function, the buffer I mentioned here. We terminate it, we add a null to the end so that we can properly emit it at the line number 30 using printf function. We are terminating this buffer with null value at line number 28. This line is referring to line number 28, this message. So we are terminating it with null value, and then we are emitting or displaying the value of the buffer variable. So detailed view. While a pipe function is the majority of the pipe model, there are a couple of other functions like pipe. This function create a new anonymous pipe. DUP, that is dup, create a copy of the file descriptor, that is duplicate. Makefifo, create a named pipe. A pipe is nothing more than a pair of file descriptors. That is interesting observation. And therefore any function that operates on the file descriptors can be used. This include but not restricted to select, read, write, function control, FCT, FCNTL, then FR open, and all other functions which are applicable to file descriptors. The pipe API function. The pipe API function create a new pipe represented by an array of 2 file descriptors. The prototype is integer, pipe, and the file descriptors. The pipe function returns 0 on success and -1 on failure, with error number set appropriately. Again highlighting, this is a variable which was referred in the previous example as well, previous session as well. On successful return, the file descriptors array which was passed by reference is filled with 2 active file descriptors. The first element in the array is a file descriptor that can be read by the application, and the second element is the file descriptor that can be written to. I introduced the concept of file descriptors in previous topic also. I talked about it in very general form, that there are 3 file descriptors we use in Linux. 0 for standard input, 1 for standard output, and 2 for error. So we are specifying the file descriptors here, and pipe is nothing but a set of file descriptors. Pipe model with 2 processes. Now this is an example where we are creating a pipe, integer, the pipe, 2 values, the size, pipe, character buffer, constant character size, a test string, and then memory set, size of the buffer, setting of the memory, and this is the pipe function implemented here. If the pipe is equal to 0, that means if it is opened successfully, then we are forking another process. We are making a fork call to create another process. That is important call here. In this application, we'll create a pipe at line number 17 and then fork our process into a parent and a child process, that is line number 18. These are the 2 lines I was referring here. As at the child, we attempt to read from the input file descriptor of our pipe. That's happening in line number 19. Return equal to read the pipe and file descriptor, buffer, the size, which suspends the process until something is available to read, which essentially means that when you run this program, you have to open another terminal window. You have to run the program in 2 terminal windows, because the program is suspended until something is available in the buffer. and you are running in the program, therefore you cannot continue with the same terminal window. When something is read, we terminate the string with a null and print out what was read. The parent simply writes a test string through the pipe using the right file descriptor, that is array of set 1 of the pipe structure, and then waits for the child to exit using the wait function. PID wait null. This is what we are waiting and we are writing to the pipe. So this is what is happening. Pipe model with two processes. Note that our child process inherited the same program continues, inherited the file descriptors that were created by the parent using the pipe function, and then used them to communicate with one another. Once the fork function is complete, our processes are independent, except that the child inherited features of the parent such as pipe file descriptors. Memory for the two processes is separate, so the pipe method provides us with an interesting method to communicate between these two processes, parent and child. Once the process finishes, the resources associated with the pipe will be automatically freed. However, we should terminate, we should close, we should free the memory by calling the appropriate function. It's a good programming practice to close the descriptors of the pipe exclusively by calling the close function. Close my pipe 0, my pipe 1. So we are closing both the pipes. If the right end of the pipe is closed and the process tries to read from the pipe, a 0 is returned. This indicates the pipe is no longer used and should be closed. If the read end of the pipe is closed and the process tries to write to it, a signal is generated. This signal is called a signal pipe, SIG pipe. That's called pipe signal. The duplicate and DUP and DUP2 functions. The DUP function or dup function or duplicate function allows to duplicate a descriptor. We pass an existing descriptor and it returns a new descriptor that is identical to the first. This means that both descriptors share the same internal structure. The function prototypes for this dup and duplicate and duplicate 2 are, first of all, you have to include the file unistd, then integer dup, duplicate and duplicate 2. For example, we perform an else seek into the file for one descriptor and file position is the same in the second. Simple use of duplicate function is illustrated in the next code snippet, like fd1, fd2. We specify file descriptor. We create duplicate of this using dup. Creating a descriptor prior to fork call has the same effect as calling duplicate. The child process receives a duplicated descriptors just like it would after calling the duplicate function. These two functions, the dup2 function is similar to dup function but allows the caller to specify an active descriptor and the ID of a target file descriptor. Give me a second, team. So this function is similar to DUP but allows the caller to specify an active descriptor and the IDs of a target descriptor. On successful return of DUP2, the new target descriptor is a duplicate of the first. And this is example of a DUP call. Integer old FD. Old FD is open and this is old FD, and now this is dub2 calling the second function old FD and 1, and close that. We open a new file called application log and receives a file descriptor called fd1 in this case. We call dup2 function with old fd and 1 value as we are passing here, which has the effect of replacing the file descriptor identified as 1, that is standard out as I told you, and old fd that is our newly opened file. Anything written to standard out will now go instead to the file named app log. We close old FD directly after duplicating it. That's given in the last statement. So this is the explanation of every statement we used in this example. This does not close our newly opened file as file descriptor 1 now references it. So these are examples of DUP and DUP2, duplicate and duplicate2 functions. So here the same function we are creating, and conditions and simple fork call duplicate2 using this standard out, and we are creating the duplicate. This is a duplicate2 function created and being used in this example. So we are forking our application into the child, line number 13 to 16. Starting 12 to 15 to be precise, and parent line number 19 to 20, that is here 19 to 20. In the child, we begin by closing the standard output file descriptor, that is line number 13. We close this standard output buffer here, standard output file descriptor. The child over here will provide ls-l functionality and will not write to standard out, but instead to the input to our pipe, redirecting to using DUP function call. That's what is given here. Execute CLP ls-1 n. So this is the call which is being used and which is explained here in this point. At line 14, we are using DUP function 2 to redirect the standard output to our pipe, that is PFD1. Once this is done, we close our input n of the pipe as it will never be used again. Finally, we use our xclp function, that is what executing here, xclp function, to replace the child image with that of the command ls-l. Once the command executes, any output that is generated is sent to the input. The receiving end of the pipe, the parent plays this role, and it follows a very similar pattern. The way we are reading, the way we are writing, we follow the same pattern. We first close our standard input descriptors at line number 19, and we use a DUP2 function again at line number 19. I am talking about the same example which is discussed here from line number 19 to this. I am referring to these lines now. Same pattern. To make the standard input and output end of the pipe, this is the code which is referred here. We close the standard out end of the pipe. In fact, this line number 19, this is done by making the file descriptor 0, that is normal stdin, to the same as PFD0. Finally, we use execute CLP the command wc-l, which takes as its input the content of the pipe in line number 22 is here, this line. So that's what is happening. So what we have done in this 3 slides, we have implemented the command discussed in the first slide, wc-l, ls-l. We implemented the same thing using the named pipe through our program. That means we have gone inside the program, we have understood how actually it is working. In this application is that our child process redirects its output to the input of the pipe, and the parent redirects its input to the output of the pipe. Very useful technique that's worth remembering here. The mkfifo function. The mkfifo function is used to create a file in the file system that provides a FIFO functionality, also known as named pipe. The pipe discussed so far, they were anonymous pipe, directly reading and writing. Named pipe, actually now this is the named pipe topic. They are used exclusively between a process and its children. The named pipes are visible in the file system and therefore can be used by any process. Function prototype of mkfifo make file system make pipe defined as include systype.h and then include sysstat.h, and this is the function mkfifo constant character path name model t mode. The mode is defined. mkfifo command required 2 arguments as were mentioned. The first was path name. This is a special file in the file system that is to be created. The second is the mode that represent what type of pipe you are creating, that is for read or write. What type of permissions you want to specify to the pipe. So mkfifo, this command returns 0 on success, -1 on error. Now example of creating FIFO using mkfifo function. So integer return value mkfifo, this is a temporary file name which is created as a pipe, and these are the permissions 066. First digit is a special digit 44 as set user ID SUID. 2 is for set group ID SGID. 0 is for sticky bit, that is for first digit in Linux, and these second number is for user, third is for group, and fourth is for others. Now for users we have read, write and execute, R for 4, write for 2 and execute for 1. Similarly for group we have read, write, execute. For others also we have read, write, execute. So if we add these octal numbers we get the respective permissions. So that means 4 plus 2 6 means read and write. So these are the permissions how it works in Linux. So 0666 means no special permissions. Read and write for group, read and write for users, read and write for others. No execute permission to anybody. If return is 0, then successfully created, else fail to create the name pipe message. This is just a snippet, not the complete function. Example is coming up in the next. In this example, we create a FIFO named pipe using cmd pipe in the temp folder. We can then open this file for read and write and communicate through this. Once we open the named pipe, we can read from it using the typical IO commands, which we will be doing, and we'll be seeing that in the example coming up after this discussion. For example, here's the snippet reading from the pipe using fgetS. So fopen, open the file for read, get the content from the into the buffer, size of this from this pfp, that is pointer which we created for the pipe. We could write to the pipe using the snippet PFP fopen for write purpose, and fprintf, that is print to the pipe, and this is a text string, and this is the pointer we are specifying here, PFP. This is pipe pointer, pipe file pointer, that's the abbreviation used in this names. That's what's interesting about the name pipe, which we'll explore in the discussion of the mkfifo system command, is that they work in what is known as a randageous model. A reader will be unable to open the named pipe unless a writer has actively opened the pipe and other end of the pipe. So which means in example we have to open the two terminals, as I referred earlier. In the named pipe we have to open the two terminals. In one end we will be writing and another end we will be reading. The reader is blocked on the open call until the writer is present. Despite this limitation, the named pipe can be useful mechanism for inter-process communication. The commands pipe model for IPC, mkfifo, what we have used, what was discussed, is one of the two methods of creating a named pipe. FIFO special 5 at the command line. Mkfifo, that is mkfifo, options and the name, where the options are -m for mode, that is permissions, and the name is the name of the named pipe to create. If the permissions are not specified, the default is 0644. mkfifo, the file name, we can adjust the options simply by specifying them with -m option, like remove the pipe or change the permissions. For example, we are changing the permissions here using -m for this pipe. It's as good as a simple file. If you notice, this is nothing but more than this is a file. We are writing to the file, we are reading the file, but this file is of type pipe. We can communicate through this pipe via the command line. On one terminal, we attempt to read from the pipe using cat command, cat file name. On typing this command, we are suspended and waiting a writer opening the pipe. That means you have to open another terminal window, and then you have to write to this file, and then you will be reading that. In another terminal, we write to the named pipe using the echo command, like echo hi cmd pipe. So we write to this file. So we have two terminal window open here. In one terminal window we are reading, and another terminal window we are writing. So the output will be something like this: cat cmd pipe hi will be what we'll be getting on the first terminal window. That's what the complete example is. Named pipe can also be created with the mknode command, along with many other types of special files. We can create a named pipe as mkfifo before by using this command mknode and the file name, that is command pipe, and this p option, where the named pipe cmd pipe is created in the current subdirectory with type as p, that stands for named pipe. So what we have learned in the session, we took a very quick review of anonymous and named pipes. We reviewed application and the command line methods of creating pipes, and also reviewed typical input-output mechanism for communicating through them with examples. We also reviewed the ability to redirect input-output using duplicate and dup2 commands. While useful for pipe, these commands are useful in many other scenarios as well, whenever a file descriptor is used, such as socket or a file. That's all for this session. I'm sure there was something new for you. I don't know to what extent, but yes, I hope that something was new for you, and for others it will be a new topic. For someone it was refreshers.